Hey everyone, welcome back. We're going to talk about pistons and the related components today. So a piston is one of the highest stressed components to an engine. Diesel fuel can burn at a flame temp of 3,900 degrees Fahrenheit, 3900. You also have to withstand cylinder pressures of up to 3,000 or even sometimes 4,000 psi of cylinder pressure during a combustion event. So a piston really needs to be built extremely well to be able to handle that extreme amount of heat and pressure. So first off, we'll look at the different areas of a piston, and then we'll talk about some different designs and the pros and cons to those designs. So here we've got the piston crown on the top here, all the way down to the start of the ring belt, which would be your top ring groove to your bottom ring groove, or your compression ring groove down to your oil control ring groove. And below that, you have the skirt of your piston. The skirt is what's going to slide against your cylinder and stabilize that piston from doing a rocking motion going back and forth as it rides up and down that cylinder. So to look at a few different types of a piston, first we're going to talk about a trunk style piston, which would be the same style we were just looking at here. Trunk style piston is going to be an aluminum alloy piston design, going to be pretty round in shape, pretty unilateral length there. Here's another one here. It's not in quite as good a shape. Very similar design, as you can see. And another similar design to that is the slipper skirt. So these trunk style pistons have gotten shorter and shorter throughout the time they've been used as the aluminum alloys get stronger, a little more rugged. And then a slipper skirt piston is going to have more clearance on the sides here, be cut a little higher up, so that you can get more articulation of that connecting rod before it hits the skirt of the piston there. So why would you need a slipper skirt? Why would you need more articulation of this rod to go side to side? Slipper skirt pistons are primarily used in a V configuration of an engine. So a V6, a V8, a V16, a V20. They may all have a slipper skirt piston because that rod is going to need to go further over as it's going up in its V formation to be able to make it up that cylinder. As we progress through time and technology, we moved on to the articulating piston. An articulating piston is a two-piece design. You have your steel crown. You've got your wrist pin here that has pressed in bushings, similar to a bearing. And then you should have an aluminum skirt that slips around that, and your wrist pin goes through it. Unfortunately, I can't find myself an aluminum skirt for the articulated piston. So if you can just imagine that the rest of this skirt here, cut it off right about there, and you would have just a skirt sitting there that you could drop right down this, and then it's held in place by this wrist pin itself as you press that through. So the benefits to the articulating piston is you have a steel crown, so it can withstand higher temperature and pressure, and you have a shorter space between your top ring and the dome or the crown of your piston. That also qualifies as a low crevice volume, LCV. The crevice volume is the amount of space between the top of your crown and your first ring here. So the less space there is, the less volume you're wasting, the higher your compression ratio stays, and the less carbon that can build up on your cylinder liner. They've also found fuel economy boosts of about 5% and the benefit of lowering your hydrocarbon emissions by up to 50% using an articulated piston. Hydrocarbon emissions, you know, that's always a big battle. Here we've got a cutaway of an articulated piston, so you can see how hollow those things really are. They're not all that heavy. You can have oil cooling in there. The more surface area you have, the better this piston can cool itself. So now that we've talked about an articulating piston, we're going to talk about a monotherm piston. A monotherm is the most recent design. It's also a steel piston. It's also an LCV, a low crevice volume piston. Because this is made out of steel, it expands at a lesser rate than aluminum does, so it can have a tighter tolerance to your cylinder. That means you don't have to wait as long for the engine to warm up before you load it down. If you have an aluminum piston, it needs to expand. Therefore, when you first fire up your engine, you can have a little bit of piston slap, where the piston can actually wiggle back and forth a little bit in there and cause a light knocking noise. So these monotherm pistons are steel, therefore, like the crown of the articulating piston, they can withstand higher temperatures and pressures. They were originally only used in large bore engines, so 15 liters and up. Now these things are becoming pretty standardized in even medium duty engines too. They've got a smaller skirt on them, so they create less wear because there's less friction against your cylinder wall. These skirts here are actually phosphate coated to further reduce friction, as you can see there. And another benefit, this wrist pin, there's no bushings in here. So again, less expensive to manufacture. If we pull this wrist pin out, you can again see a phosphate coating down in there to prevent friction, to reduce friction without adding manufacturing costs. This wrist pin is a floating wrist pin. It's not a press-in. You can see this one's floating too, because the pin spins while the rod's not. Most diesel engines are going to use a floating wrist pin design. More expensive manufacture, but a better design overall. So the disadvantages to the aluminum piston is the low melting point. 1250 degrees is what just regular old aluminum can melt at. Now these are usually used in a hyperrutectic design. Hyperrutectic means that there is more of the alloy in there than there is the base material. So a hyperrutectic piston is actually going to have about 16 to 20% silicon. This is going to combat thermal expansion and melting. However, you can still melt down an aluminum piston. This is a piston that came out of a common rail engine that had an uncontrolled fueling event. So this piston used to look much more like this guy here. Look at that bowl depth. So this is the piston bowl, and that's where that injector is firing. Most diesel pistons will always have a piston bowl for the injector to fire into. That bowl will not always be centered. That bowl will end up where the piston is. Therefore, the way that you orient these pistons is very critical when you assemble your engine. Pay attention to any kind of identification marks pointing forward. So another disadvantage to the aluminum piston, besides the ease that it can melt at, is that because that top compression ring sees such high pressures, it would actually wear away extremely fast. That groove would wear away because of the hardened metal of the steel ring. Therefore, they have to install stainless, also known as nickel, inserts for this top groove. That's what you can see that I'm actually spreading or wiggling here. So that adds to the manufacturing cost because they had to inject this stainless groove around the top of the piston here. You can see that in this one too. There's the beginning of your stainless insert, there's your ring, there's the top of it. So every aluminum piston, you're gonna have your stainless inserts there. That adds to the manufacturing cost. So we'll lead into rings from there. Talking about our top ring is going to be our compression ring. The compression ring oftentimes is built in a barrel formation. So the face of it has a little bit of a barrel dimension to it where it swings out a little bit. Those rings are actually honed into place, and then you can look at the wear on it to determine how worn out these rings are. So top ring is your compression ring, middle ring is your intermediate ring, sometimes also called a compression ring. Your compression ring is going to seal your cylinder. It's going to try and keep all this compression up top. As your piston is coming up, you can still see the spray pattern of the injector on this one, which is pretty neat. As your piston's coming up, that compression is going to try and blow down and around it. As it blows down and around it, it's going to follow this crevice volume surface, and it's actually going to go behind that ring and help push that ring out and seal it against the cylinder wall. Your intermediate ring also is going to have some sealing properties. It's going to be built at a tapered this way to help your compression, and it's going to help with oiling. Finally, you get to the bottom ring here, your oil control ring. This is often a 3-piece ring with a top and a bottom, but not always. As you can see, this is only a 2-piece. The top and the bottom have become one, and then you also have your coiled expander ring. So this coiled expander ring here just traps all the oil in it. And then this guy keeps it in place and keeps the expander from coming apart too much. You can see all the holes within it, and that's to allow that oil out and to keep that cylinder wall properly lubricated. Stay tuned and we'll talk about some connecting rods.